Okay, let G be a group, and we'll start using A inverse to denote the inverse of an element A of the group G instead of A primed. Previously, we saw that the inverse of AB is B inverse times A inverse. It's not in general equal to A inverse times B inverse because the group might not be commutative. Okay, so then in this brief lecture, I'm going to talk about this theorem that says, let's fix an element G of our group, and then this map called conjugation by G that takes an element X as input, or X is in the group, and then the output is you multiply X on the left by G and on the right by G inverse. So here's another way to write it. Cg of X is equal to gx G inverse. This is called the conjugation by G of X. And the theorem says that this is an isomorphism of groups. And the goal of this theorem is to show how to prove something is an isomorphism of groups. This theorem isn't going to be particularly important for our course, although later on in more advanced courses, such an isomorphism is called an inner automorphism of the group, and so it does come up very frequently. You might have seen this conjugation action appearing in a linear algebra course. Another point I want to make is that if the group is abelian, then this isn't a very interesting result, because then we can flip the order of the X and G inverse. So we get G inverse X, and then the G inverse cancel, and then we just get X. And so this map is just the identity map, namely it sends X as input and the output is X. And that's obviously an isomorphism. Okay, so with that out of the way, let's go to the proof. So we want to show some map is an isomorphism of groups. So there's two things involved in that. First, we have to show that the map is a bijective map. In other words, as on the level of sets, it's injective and surjective. Injective, another term for that is one-to-one, and surjective, another term for that is onto. And then in addition to being bijective, an isomorphism is what needs to be a homomorphism, and we'll get to that later. What I want to focus on is how to prove a function is bijective, or let's start with how to prove it's injective. Again, here's a picture of a function that's not injective. It sends two different elements in the input to the same thing. We want to show that that does not happen. And so the way to prove a function in general is injective is you suppose you have two elements in the input, x1 and x2, such that the output is the same. So suppose Cg of x1 is equal to Cg of x2 for some x1 and x2 in G. And then what we want to show is that x1 and x2 have to be the same. They weren't different, even though in this picture they're kind of implicitly drawn as different things. Okay, so here's our hypothesis or assumption. And then substituting in what Cg does, that's conjugation by G. So you multiply by G on the left and G inverse on the right. Ditto for here. And then because we have cancellation, both left and right cancellation in groups, we can cancel the G and the G here. Equivalently, we can multiply both sides of this equation by G inverse. Likewise, we can cancel the G inverses on the right, and so we finally get x1 equals x2. So we've shown that this map Cg is injective. Next, let's show that this map Cg is surjective. So this picture for surjective is if you start with any arbitrary element y on the target side, or codomain side, then you want to find an x in the input side that maps to y under the function. So let y be an element of G is how you start the proof. We need to find an x in the group such that the function Cg maps x to y. So Cg of x is equal to gx G inverse. So we want to find an x such that this equation holds. Since we're trying to find x, well, let's solve this equation for x. And doing so, it's just like in algebra. We multiply on the right both sides of the equation by G. The G inverse and the G then cancel on the this side of the equal sign. Similarly, do the same thing with canceling this g by multiplying both sides of the equation by g inverse. And we get that x has to equal this thing. And so then let's check if this value of x works. Well, we compute the conjugation by g of g inverse y g, which is what we found x has to be. And doing that, we get indeed that the output is y. So we've shown that this function CG is surjective. Next, we have to show that CG is a homomorphism. And the definition of a homomorphism is that it's a function that when you apply it to x times y, where again the times is the operation in the group, in some examples it might be plus, but okay, that the result is the same as if you apply the function, in this case CG, to the elements x and the elements y, and then compute the product of those two elements. Okay, so let's work on both sides of this equation separately. So CG of xy, what's that? Well, that's just conjugation of xy by g. So you multiply by g on the left, g inverse on the right. Okay, and then let's now analyze this right-hand side. The conjugation by g of x is g x g inverse. Conjugation of y by g is g y g inverse. Then when you multiply these two, the g inverse and the g, they cancel. And so they turn into the identity disappears because x times the identity is x and so forth. And then, well, what we're left with is this, and that does happen to equal what we've started with. So that proves that this equation is true. I've kind of worked backwards. Perhaps when writing the proof, you should be a little bit more careful in saying that you don't know at this point up here when you write this equation that it's true. You're hoping it's true and hoping to establish it's true. And the work down here shows that this equation indeed is true. We did not start by working or doing things to this equation. We just separately identified or analyzed the two sides of the equation and showed that it's true, or show that those two sides are equal. Perhaps I should have written a question mark when I wrote that equation.